Okay, let's go over homework 4. This question is asking for what? What are we looking for in this question? We're asking about how much heat, correct? So if I'm looking for heat, what unit am I looking for? I'm looking for calories. Okay, so of the numbers that I have written up here, the only number that has the calorie unit in here is the specific heat. So that means I need to use that equation, or that number somehow, to calculate out my my heat for this problem. So since I'm looking for heat and I want the calorie unit, so I'm going to write 0.22 calories per gram degree C. Why am I writing it like that in the railroad track? Second?
So we can cancel out.
I need the unit calories, and I need the unit calories to be in the numerator when I'm finished. And so I put it in the railroad track in the numerator. The only problem is that calorie unit that's in the numerator also came with a couple of other units that are in the denominator, right? So what do I do with those guys? I need to cancel those guys out. So I'm going to throw 75 grams in the numerator up here, and that allows me to cancel the gram unit out. And then you need to cancel out that degrees C thing. The one thing we have to remember about this is specific heat. And what is specific heat a measurement of?
The end minus the beginning.
What?
How much it takes 1 gram of water to heat?
That's the definition of a calorie. So I still don't have it.
It's how easy it takes heat to do it.
Sure, how easy or hard it is to heat or cool something off. So we're talking about something's temperature changing. So do I get to just use the initial temperature or the final temperature for these problems? No. So in this problem right here, I'm talking about how much heat was added. So if I added heat to this aluminum, then its temperature must have changed. And if I added heat to it, then I increased its temperature. So my initial temperature is 3 degrees, and my final temperature is 110 degrees. So then I'm working with the change in the temperature. So it caused the temperature to go up to 110, but it didn't start at 0, it started at 3. So my change in my temp is 107. So then I would drop a 107 here, degrees C, cancel that out, and then I end up with calories as my only unit left. David, what is that value? Everybody should already have turned their homework in.
Oh, I got 2 over here.
I only want the one that's done.
Copies that they get.
So 0.22 times 75 times 107, I get 1765.5. And is that the right answer? We okay with that?
Don't you need to add a 0?
No?
So then that's the original one that I got.
There's only 2 significant figures with this problem, so I can't use the entire number. So, answer?
18.
18, just 18? The answer is 18?
18 calories.
Kcal.
It's 18, it's not 18 kcals either. You're off by 10. Say again? I only get to use two sig figs, so these are the only 2 that I can use.
Can you do 1.8 times 10 to the
You could either go 1800. Why is that not the best way to do it? It's obvious that the final 0 isn't significant, correct? There's no decimal place. But what about the 0 preceding it? Do you know if it's significant or insignificant? You don't, the way this is written. In this case, it is insignificant, so we wouldn't want it to be thought of as significant. So the way we could rewrite this would be 1.8 times 10 to the 3rd calories. That would be perfectly acceptable. So how many sig figs do you see in that 1.8 times 10 to the 3rd? 2. That's blanketly obvious. 2.
Is the 1,800 calories wrong?
18 isn't wrong, no. It's not as satisfying. to the reader. To the reader, they're like, what about that 10 spot that's bugging me? Is that significant or insignificant?
So is there an advantage over that or 1.8 kcal?
Nope. 1.8 kcal is fine. How come 1.8 kcal works? What's K mean? What's K means 1,000, so what's 10 to the third mean? 1,000. So they're completely interchangeable with each other. So if you put 10 to the third, fine. If you put K, fine. Either of those work. Okay, so this next one, I like it, but a lot of people don't. The issue with this problem is you have to think about two things. The best way to do a problem like this, in my opinion, is to draw yourself a little picture. So I've got myself a little chunk of lead, and this little chunk of lead is going to go into a container of water. And what happens to the water's temperature? The temperature goes up. So what's that tell you about the lead?
So it's really hot.
Well, not that
It's warmer than the water.
it's got to have a higher temperature than the water's temperature, right? Okay, so the lead is warm, the water is relatively cool. We know that it's 11 degrees Celsius, and that's relatively cool, right? 11 degrees, would you want to be outside if it was 11 degrees? If I was, I'd want to have a hat on and a jacket, right? Some shoes, I'd probably be good. Pants, I suppose. So I put this piece of lead into the water, and the water's temperature goes up to 22 degrees. Okay. So we know the lead is hotter. So what happens to the amount of heat that the water has? It goes up, right? It has a certain amount of energy. I put this hot piece of lead in it. Now it has more energy. I know that because the temp goes up. So what happens to the heat in the lead? It goes down. What can you say about those two heats? They're equal but opposite. So if the water's heat went up by 1,000 calories, then the lead's went down by 1,000, so its Q would be negative 1,000. That's the first thing that you should have realized. That whatever heat the water gained, the lead lost. It came from somewhere, and it came from the lead, not from the surrounding universe, but the lead. So that means since the conservation of energy states that you can't create nor destroy, so the lead lost it, the water gained it, so those values must be equal to each other. So if I know the Q of the lead, or the water, then I also know the Q of the lead. In this problem, we're trying to figure out what the temp is of that lead before it goes into the water. Yeah.
Where did you get the Q?
I haven't figured it out yet.
Oh.
We're going to in a sec,
So
though.
you just made up 1,000?
I just totally made up 1,000. Yeah, that's not what it actually is. Then there's one other thing that we know without the given information. So the water's temperature starts at 11 and then it goes up to 22. Why doesn't it go up to 23?
Because there's a tier, that's the first go.
I know, why?
22 is when the two, they're equal.
Okay, so at 22 degrees, the water reaches 22 at the same time what? The lead reaches 22. So once they're both 22 degrees, then there's no more heat transfer. So what do we know, what piece of information do we now know?
That's final temperature.
We know the lead's final temperature. So we know lots more information than we think we know when we start this problem. Okay, so if I was you guys, I would probably do something like the lead is here, and I know the lead is 75 grams. That's my mass, and I know the temperature final of the lead is 22 degrees Celsius. We okay with me saying that? We just figured that out, right? And I know my water. Oh, I also know that my specific heat of the lead is, I know that the specific heat of the lead is this 0.038, and this thing was in the notes, so 0.038 calories per gram degree C. And so for my water, my mass is 175 grams, and my temperature initial is 11 degrees C, my temperature final is 22 degrees C, so I can just do my temperature change of 11 degrees C, and the C of my water is 1 calorie per gram degree C. So I know a lot of information about the water. I know pretty much everything about the water, don't I? What can I calculate for the water? I can calculate the Q. So the Q is heat, and that's calories that I'm looking for. So I'm going to throw 1 calorie per gram degree C. That way I get a calorie unit in the numerator. Then I'll throw my 175 grams in the numerator so I can get the grams to cancel. And then I'm going to throw my change in temp, which is 11 degrees Celsius, and that cancels. And then when I do that, I get a whatever 11 times 175 is. It's like 19 something or other. 1925. So 1925 calories. That is how much heat the water gained when the lead hit it. What do we now know? How much the lead lost. So what's the Q of the lead? Minus 1925 calories. Negative. Are we okay with that? Some heat was transferred. Somebody gained, somebody lost. So the lead's value for its Q has to be negative. Okay, so now we're still trying to figure out this change in temperature. So I need a degree C. So with the other pieces of information out here, I can calculate out a degree C. So I'm going to start by throwing grams, degrees C, 0.038 calories in my railroad track. I'm doing that because I need degree C. My answer needs to have degree C in it. So I need to get rid of the grams, and from the problem it's 75 grams. So my grams cancels out. And then I can use my negative 1925 calories to cancel out this calories in the numerator, and I can get myself a degree C. And it looks like that works out to be negative 675 degrees C. What did we just calculate?
Temperature initial?
No. Does that make any sense?
Temperature change.
Temperature change, right? This couldn't possibly be initial temp, right? Because that's like way below absolute zero. Plus this thing was hot, so couldn't be initially really cold. So what do I do to get my final answer? This is how much the temp changed. Does this number make sense? Why not? No, it's not. It's not cold. Its temp changed that much. So? We're trying to figure out the initial. So we can use the equation, but I'm trying to get you to like see it's not a big deal.
Yeah.
No?
This is just how much the temperature dropped.
This is just how much the temp dropped. So you either have two choices. It was room temperature and it's now really, really cold, or it was
675 degrees.
it was started really hot and then it lost 675 degrees of heat. Is that reasonable? If I took a chunk of lead and put it into a Bunsen burner, it'd get to about 700 degrees. So that 700 degrees, if I dropped a 700 degree chunk of lead into some water, what would happen? The lead would cool off, the water would heat up, and they would stop when they reach the same temp. That's exactly what's going on here. So this 675 is my change in temperature. If we go to the equation, delta T equals temperature final minus temperature initial, we're trying to get this temperature initial, correct? So if I rearrange this thing algebraically, I get temperature initial is equal to temperature final minus the change in temperature. That's okay, right? My final temperature is 22 degrees, right? And my initial or my change in temperature is negative 675 degrees Celsius. So is that okay? So what was the temp before it hit the water? 697? 697 degrees Celsius. I guess we'd probably have to say it was 700 degrees Celsius, or 7.0 times 10 to the second degree Celsius to get the correct number of sig figs, which is 2. But it's about 700 degrees Celsius. I drop it in. So think about that for a second. I have something that's 700 degrees Celsius, and I drop it into something that's 11 degrees Celsius, and that thing's temperature only goes up to 22 degrees. How could that possibly be? Shouldn't something that's 700 degrees, when it's put into something that's 11 degrees, shouldn't the temperature of the two things be like 350? Water specific heat is hundreds of times more higher than that of the lead. It's 1 versus 0.038. So what you're looking at is the fact that water is hard to heat and lead is not hard to heat. Right? Do you see that exhibit? They always have like standing exhibits at OMSI, and there's like a really bright, like 100-watt light bulb there, and underneath the 100-watt light bulb there's a piece of wood and a piece of aluminum, and you touch the piece of wood and it's warm but it doesn't burn you, and then you touch the piece of aluminum and it actually burns your fingers. Why is that? The specific heat of aluminum is low, which means it heats up really fast, but it also gives away its heat really fast. So when your hand touches it, the aluminum's like, here, take this. When you touch the wood's like, I'll just hold on to this so you can have a little bit of it. But that's the situation with the water. The water's got this mass, plus the other problem with this is that the water's 100 grams more than the lead is. I got 100 grams versus 75 grams. So the water doesn't heat up very much because it's specific heat. It's very hard to heat that water, where the lead it's very easy to lose its heat. Somebody had a hand up.
It was me, but I saw it. You wrote the temperature in scientific notation. That's okay.
Oh yeah, absolutely. And it's just another way to write a number.
Okay.
Could you walk through the significant figures on that? Because I was thinking that the specific heat is exact, and 75 grams is exact.
11 and 2.2 and 22 are both 2. Right?
Okay. Gotcha.
You don't have to worry about the significant figures for the specific heat things, because even though the book says like 1.0, it's actually its definition is 1, so it's got a zillion zeros. And the 0.038 for the lead, there's actually like 12 zeros after, or 12 numbers after that, because they've studied it so much. So those things aren't going to be an issue for you, but you do have to worry about the 175 is 3, 11 is 2, 22 is 2, and the 75 is 2. So we've got 2 sig figs for your answer.
Gotcha.
Does it make a difference, like, when you determine your significant figures? Because, like, when I did
You
my
only
math-
do sig figs for your final answer. That's it. And when you start sig figging all the way through the problem, at the end your answer turns out to be incorrect. Yeah, it's going to be off. Sig figs apply to the very final, here's my answer. And so once I go to write this, once I got this 675, not until I got this, 697, once I got that, that's when I went back and looked to see what sig figs I needed to worry about. Last thing you do. You could have done something else. And if math is not an issue for you, you could have just done that. Set the equations equal to each other. You actually know this, 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 and you're looking for that.
Do you have to set one side negative?
You do need to set one side negative. You can flip-flop those guys.
The temperatures?
Actually, it really doesn't matter if you understand what you're doing. If you don't set one negative, your answer will be negative 700 degrees Celsius, which doesn't make any sense, right? But since you know this was something hot that goes in, then okay, well, it's obviously this thing was 700 degrees Celsius. But each of these pieces were given, and so or figured outable, and that's the only one that we needed to calculate. So if the algebra is no big deal for you, go ahead and do it this way. It doesn't really matter. Okay, so let's talk about so what makes the Greek and Dalton's theory of the atom really important to science? Why are these atomic theories sort of like the most important thing to happen to science in forever? True, they were right, mostly right, not completely right, but mostly right. That's not the big issue.
This was more evidence.
Mm.
Evidence to back his theories.
This was evidence.
No, that was just a belief.
How about this one?
This was he had evidence.
He had a little bit of evidence for the last two things,
Mhm.
but not for the others. Yeah.
It got people to start questioning it and to experiment to see if they were right.
Okay, it gave people a method of checking things. Because prior to that, what was going on?
They were just saying what they thought.
They're making stuff up. Well, these guys were making stuff up too, right? It just turns out that these guys making stuff up turned out to be correct. So the other people that made stuff up, do you have, like, what was the theory of what things were made of when the Greeks were making up this theory of the atom? Oh, sure. Yeah, absolutely. That one's always, can always say that one, right? How about what those things were made of?
Oh, the elements.
They were infinitely small, like you could keep going. What, sorry.
No, like, what's that, some cartoon my sister made me watch.
Your sister made you laugh.
It was called Avatar. And then they made a movie out of it called The Last Airbender. So what do the Greeks think everything's made of? Air, fire, water, earth. So that's what people thought everything was made out of. Which, okay, air is something, and earth is something, and water is something, but fire isn't even anything. It's just the observation of a chemical reaction occurring. So it isn't anything, and for you to be composed of fire is a little ridiculous. Of the other things, I suppose, in a roundabout way, they were right, but they were completely wrong in how they were thinking about it. But at that time, they were talking about things like the four elements that everything are made of. Other things that were going on at this time were the alchemist guys who were trying to convert like lead into gold. Obviously not something, but if you have no education and somebody tells you that this is the way things are and they show you something, you're pretty apt to believe what it is that they're talking about. These guys here, this is
Probable.
provable. You can start proving these things, right? It gives people a line of thinking to then do experimentation on. Before that, there wasn't anything to go on. It was mysticism or it was religion. This is something that you can actually check. So are things made of earth, fire, air, and water? How do you check that? How do you pull fire out of a person? Yeah, it doesn't work that way. And along that lines, no, people can't spontaneously combust. It's completely impossible. Okay, neutrons, or protons, where do we find those things? These guys are in the nucleus, right? And the electrons? They're in orbits. Now, the key word to this next question is the magnitude. What can you say about the magnitude of the charge of the proton relative to the charge of an electron? It's not. They're equal to each other. The negativeness in an electron is equal to the positive in a proton. Even though the proton is massive compared to the electron, their charges are equal and opposite. So they are equal. The electron is -1 and the proton is +1. They cancel each other out. Chemical reaction, what occurs? Dalton.
It's rearranged.
Yeah.
A or E?
I
Separate.
don't know. I'm both.
A? That's all that happens. The atoms become separated, they become combined, or they simply rearrange with each other. And in your head, you should be thinking about like two Lego structures. Somebody disassembles and makes more Lego structures out of them. Nothing happens to the Legos, and nothing happens to these atoms. They just hook up with different atoms. Why is Dalton super happy to know that the water's chemical formula is H2O? It's a simple whole number ratio. It's the ratio of 2 to 1. I mean, the only more simple one would be 1 to 1. The ratios itself are very simple, and the ratios themselves are always going to be whole numbers. There will be no partial oxygen atoms. It's either an atom of oxygen, or 2 atoms of oxygen, or 6 atoms of oxygen, but never like 2.5.
What about definite proportions?
Oh, and how about this? It is always H2O. So it's a simple whole number ratio, but it's not just any old simple whole number ratio. It's 2 to 1 H's to O's, and it can't ever be anything other than 2 to 1 ratio of H's and O's. What was it that Thomson discovered that is still true today? What did he discover about the atom? Okay, so there's a negative charge. And what do you know about that negative charge? The thing can come off. The electron can come off of the atom. That's what he found out. That there's a negative charge and it can come off. The other stuff that he said about the atom turned out to be not true. But what he did discover about the atom is that there's an electron that can come off. That kind of turns out to be the most important part of this for chemistry, right? Because our definition for chemistry entailed what? Yeah, actions of electrons. Not actions of protons or neutrons or the nucleus, but the electrons. All the chemical, everything that you see happening around you, those are chemical reactions, and those are just the electrons moving around, not the protons. What was it that Rutherford discovered about the atom? Okay, so that the mass is in a nucleus, and what about that nucleus?
Small.
It is tiny. What else? It's dense. Anything else? And positive. Sort of a verification of the positiveness of it, but that it's positive. Okay, how about this defense of this answer that matter is mostly empty space? The gold foil experiment. Most of the things went through, for sure. The nucleus, this answer from above, right? The fact that the nucleus is tiny and that's where the matter is. So you could say something like nucleus here, atom here. This thing is like 10,000 times smaller than that thing. And all the mass is in that little tiny spot in the middle. So it's a 10,000 to 1 shot that you're going to hit this thing. Or you're at 10,000 to 1, nothing to something ratio. There's a little bit more to it. What's the other piece? The atom itself is kind of hollow, but what else is there? There's space between the atoms. Okay.